Hello everyone, I once again welcome you all to MSP lecture series on interpretative spectroscopy. In my last couple of lectures, I started discussion on UV visible spectroscopy, and also I started discussion on DD transitions. In case of organic molecules, invariably we come across N to pi star, N to sigma star and pi to pi star transitions, and also rarely sigma to sigma star high energy transitions. But along with these transitions, we can see one more transition, that is called DD transition, because of the arrival of d orbitals in compounds. They are called transition elements 3D, 4D, 5D, where we start with D1, whether it is 3D1, 4D or 5D1, we start with D1 up to D10. So this about 10 different type of electronic configuration we come across among 3D, 4D, 5D up for 30 elements. So they show this DD transition, and mainly the color of these complexes are responsible often due to DD transitions, and sometimes there may be some other transitions. Let us look into all those things in detail. Okay. So now let us look into the DD transition. I had mentioned DD transitions arises because of filling of electrons to the d orbital, and then if you consider octahedral complex, in a octahedral complex in a crystal field, the d orbitals remove their degeneracy and split into T2G and EG level. T2G is lower in energy, EG is in higher energy. T2G consists of dxy, dxz and dyz, whereas EG consists of dx minus y square and dz square. This is a typical octahedral field. And in case of tetrahedral, opposite of that happens. T2 will be higher in energy and E will be lower in energy. That enough information is given in my advanced transmetal chemistry for these geometries by considering the orientation of the orbitals and also approach of the ligands towards the metal. So based on that one, crystal field splitting will occur, and the energy of degeneracy of d orbitals is destroyed, and then they will be aligned into different energy levels. So in case of tetrahedral, we have dx minus y square and dz square will be lower in energy, whereas dxz, yz and xz will be higher in energy. The transition takes place between them. A typical example is shown here. If you look into hexa aqua titanium 3 plus a D1 system here. Initially it is 3D2, 4S2. We have removed the 3 electrons because the titanium is in 3 plus, so it would be 3D1 system. So in this one electron is placed in T2G. So this electron would be promoted here. This we call it as electronic transition. And you should remember, it is going like this here. And then if you consider tetrachlorocobaltate, a 4-coordinated tetrahedral complex, high spin complex. So in high spin complex, we have 4 electrons in the ground state and E state and 3 electrons in the T2 state. And now either this electron or this electron can be promoted here. You can see this electron is sitting here in this fashion. So these two are typical examples of DD transitions. Now we come across another interesting transition, that's called charge transfer transition. Charge transfer transitions are of two types. Charge can be transferred from the metal to the ligand or ligand to the metal. For example, if you consider potassium permanganate or potassium dichromate, they are intensely colored, and if you look into the manganese oxygen state, it's +7. So that means now it has 0 electrons. It has no electrons in the valence shell because it has 3d5 4s2. All the 7 electrons have been removed to generate Mn +7. So 3d0 and 4,0. So that means if this compound potassium is intensely colored, that is, you can overrule DD transition because we don't have any electrons in the DD transition. That means intense violet color may be due to something, some electronic transition. How electronic transition can happen? Probably oxygen is lone pairs are there. So it will give electrons to the metal empty orbitals. That means you can say here, due to the charge transfer, and without any hesitation you can tell that this is ligand to metal charge transfer transition. For example, if something like this, we have oxygen, and then on subject to UV light or visible light, electron is promoted from 2p to 3d. This is a typical ligand to metal charge transfer transition. And in cluster compounds, they have one or more metal-metal bonds. Color is due to either sigma-sigma star, pi to pi star, or delta to delta star. You recall the bonding concepts I explained for metal-metal bonds, where we came across one bond, two bonds, three bonds, or four bonds. When you have four bonds, we call it as delta bond, and we can also have five bonds. That's called quintuple bond. If you just recollect your understanding, if dz square, for example, we have a situation something like this. So here dz square, dxy, dxz, and dyz. Same thing is here, dyz, dxz, dxy, and dz square. It happens when two square planar complexes are interacting with respect to the principal axis. They are aligned in this way, in an eclipsed manner. In this case, something like this. So typically, so now this is interaction. So now if you consider this, d orbits are like this. So that means basically head on is there, means it's a dz square is sigma, and then we have dxz and dyz 2 pi, and then we have dxy, this is called delta, we call it as. And then similarly we have delta star for the same pi pi star and sigma star. Often we come across, in this case, sigma sigma star is very high energy and pi pi star is little lower in energy, and the least energetic is delta delta star. This is the charge transfer between metal to metal. All these transitions, if you come across, they are called metal to metal charge transfer transition. And then in diatomic molecules of non-metals such as F2Cl2 Br2 and I2, color is due to pi is to sigma star transition. In O2, color is due to pi star transition. In ionic crystals, if we see color, NaCl, LiCl, KCl, color is due to F centers, solid state defect. Many times rock salt is slightly pink in color. So here what happens, it is due to some solid state effects or some voids that are occupied by other different hetero anions or cations. Mostly it is here cations, or it can be anions as well. This is called ionic crystals. In ionic crystals, the color is due to solid defects. And of course, always the energy difference can be correlated with Hc by lambda. Delta is directly proportional to wave number, or you can write in this fashion. Okay. So now it is very easy to understand that what kind of color a substance shows, and then that is due to what? By just looking into artist's wheel here. Each color has a complementary color, the one opposite to it on the artist's wheel on opposite side. The color an object exhibits depends on the wavelength of the light that it absorbs. For example, if a substance is absorbing red color, that means it emits a green color and it appears as green. If the substance is absorbing red color, it appears as green, and if it is appearing as orange, means it is absorbing blue color. Or if it is absorbing blue color, it appears as orange. Or if it is absorbing violet color, it appears as yellow, or if it is absorbing yellow color, it appears as violet. This one should remember. So complementary color is shown by the substance when it absorbs the other color for electronic transition. So now I have given here the wavelength range observed by the substance, and also the color, and also color seen by us. For example, if a substance absorbs in the range of 380 to 430, that's violet. The color appears is yellow to green. On the other hand, if the absorbance is in the region of 430 to 480, that means color absorbed is in the blue region, and compound or substance appears yellow in color. And then again, if it is absorbing between 480 to 490, color absorbed is green to blue, and color appears is orange, complementary color. And if it is absorbing in the range of 490 to 500 nanometer, it is essentially absorbing blue green color, and it appears red here. Okay. And then between 500 to 560, a green is absorbed and it appears purple. And then 560 to 580, color absorbed is yellow to green of the light, and then we see violet. And 580 to 590, yellow color is absorbed and it appears blue. And 590 to 610, orange is absorbed, we see it as green to blue in color. But if it is absorbing between 610 to 750, So red color is absorbed and the substance appears blue to green in color. So this gives some idea about the wavelength range absorbed and the color corresponding to that one, and as a result the complementary color it displays for us. Now let us go to some technical things here, little bit of theory, not worrying too much about complicated theoretical equations or anything. We should try to understand this all due to the electrons, then how the electrons are there in the orbitals and what they do. So a little bit of information is needed in that context. So this slide is prepared. So angular momentum for single electron or atom, when we consider, we have to consider two things. One is orbital motion of the electron and also its spin. So that means orbital motion is movement of an electron in orbit around the nucleus, and then the spin is movement of an electron about its own axis. You can simply correlate this one with the sun and the earth moving in the orbital. So earth rotating about its own axis and also it is coming around sun. So one is orbital motion and the other one is spin motion. Rotating about its own axis taking 24 hours is spin, you can consider for a typical electron, and orbital motion is surrounding the moving around the sun by earth. So it is something like that. So that means momentum m into v, we know from physics. Angular momentum is mass into angular velocity and n omega. Okay. So now orbital angular momentum L is nothing but it arises due to the orbital motion of electron around the nucleus. So L equals square root of small l into L plus 1 into h over 2 pi, or it can be L equals square root of L into L plus 1 h. Well, we all know that h hash equals h over 2 pi, where L, capital L, is total orbital angular momentum. It can be 0 or positive, and L is, small l is orbital angular quantum number, or it is also called as azimuthal quantum number. So typically you can show like this, okay, electron revolving around the nucleus. Okay. Now spin angular momentum, it arises due to spin motion of electron about its own axis. So this is given by term S equals square root of S into S plus 1 into h over 2 pi, the way we gave orbital angular momentum. So S equals, you can also simplify it like this, where S equals spin angular momentum, that means ms equals plus or minus half, and S equals spin angular quantum number, that is half. So that means S can be plus half or S can be minus half. So plus half is shown in clockwise and this is shown in anti-clockwise. So now let us look into the total angular momentum quantum number J. J is a combination of both spin motion and orbital motion. So the total orbital angular momentum of an atom, capital L, is sigma L, sigma azimuthal quantum number, and the total spin angular momentum of an atom, S equals 2s plus 1, combined to form total angular momentum, a number that is quantized by the number, a term called J. L and S do not necessarily have to be pointing in the same direction, therefore they can range from L plus S to L minus S values. So J can have L plus or minus S values. It is interaction between orbital and spin angular momentum quantum numbers, how they interact, whether they couple L plus S, when they interact L minus S. This is how we term those things. So small j equals modulus L plus S or L minus S. So that means capital J equals square root of j into j plus 1 into h over 2 pi, or it can be simplified as j into j plus 1 h hash. So where small j is angular momentum quantum number and capital J is total angular momentum. So this L and S coupling is represented nicely in this figure here, and if you just look into this violet or purple conic, that shows total angular momentum J, that is purple, and orbital is given in blue. This orbital one is given in blue here, and then spin is given in, with respect to its own axis is given, and with respect to the nucleus is given in blue, and together LS coupling is shown in this purple cone. So this is how you can represent or illustrate L and S coupling, spin orbital coupling or orbital spin coupling. So now let's look into the angular momentum for multi-electron atoms or ions. For two electrons, atoms and ions, we should consider what we should do is total orbital angular momentum is nothing but the orbital angular momentum for two electrons is L1 and L. So let us say L1 and L2, and then L equals L1 plus L2, L1 plus L2 minus 1, and until it goes to L1 minus L2. This is called Klebs-Gordon series. So where L is total orbital angular momentum quantum number, it can be again 0 or positive, it was defined earlier. And then L also we know that square root of L into L plus 1 into h over 2 pi, where L is total orbital angular momentum. So now for example, let us say L1 equals 1 and L2 equals 1 and L1 equals 2 and L2 equals 2, we can calculate. And when we have this one, if we start following this rule, what we end up is we get 2 and 1 and 0 values are there. And then if you go for L1 equals 2 and L2 equals 2, we can get values 4, 3, 2, 1, 0 like this. Okay. So now let's look into spin angular momentum in the same way we looked into orbital angular momentum. So the spin angular momentum quantum number for two electrons, say S1 and S2, and again we have S1 plus S2 and S1 minus S2. This is again Klebs-Gordon series, and where S equals total spin angular momentum quantum number that can have plus or minus half, and then S is, we know that square root of S into S plus 1 into h over 2 pi. For example, S1 equals half and S2 equals half is there. What we get is at the end, using Klebs series, we get 1 and 0 values for L. So now let's look into together spin orbit coupling. So LS coupling also it's called Russell-Sanders coupling. And here if we consider orbital angular quantum number for two electrons, say L1 and L2, from again Klebs-Gordon series, we will be having L1 plus L2, L1 plus L2 minus 1 continuous and L1 minus L2 value. And same way if you consider spin also S1 plus S2, S1 plus S2 minus 1, and then eventually we end up with S1 minus S2. And for lighter elements, what we should do is J equals L plus S to L minus S we have. That means here where J equals total angular momentum quantum number, J into J plus 1 h over 2 pi, this is square of. So J is total angular momentum. See, that's how you can use it. But when we should use L plus S and when we use L minus S, we can see for JJ coupling for heavier elements, if we consider, we can see L1 plus or minus S1 and J2 is L2 plus or minus S2. If you consider J equals sigma Ji, so then it can go J1 J2, J1 minus J2 it comes. And this is how we also get square root of J into J plus 1 into h over 2 pi, and we define J as total angular momentum. Okay. So now let's come to the term symbols. A term symbol or a spectroscopic term represents the energy level of microstates with the same energy of a given electronic configuration. So here J is the total angular momentum quantum number and 2s plus 1 is spin multiplicity. So then we have symbol like this, 2s plus 1 L J, and J can have L plus or minus S. Term symbols we can write for either ground state or excited state for S orbital, P orbital, D orbital or F orbital. All the 4 orbitals we should be able to write. For example, this L values, depending upon L values, we have to give these symbols for terms. When L equals 0, S, when L equals 1, P, L equals 2, D, L equals 3, F, and L equals 4 is G, and L equals 5, H, C, L equals 6, it is I. So J is excluded in term symbols because we are using J for total angular quantum number. And unpaired electrons, for example, 0 is there, 2s plus 1 will be 1, and if 1 is there, half, it becomes 2s plus 1. This becomes 2. Okay, and then similarly, if we have unpaired electrons, 2 are there, then 2s plus 1 value will be 3. And if we have 3 unpaired electrons, the 3 spins will be there, 3 half spins. As a result, 2s plus 1 will be 4. And in the same way, if you have 4 unpaired electrons, the spin will be 2. This is sigma s, and then 2s plus 1 will be 5. When we have 1 electron, 2s plus 1 is 1, we call it as singlet state. When we have 2s plus 1 value of 2, it is called doublet state. when we have 2s plus 1 value of 3, we call it as a triplet state, and when we have 2s plus 1 equals 4, it is called quartet, and then when we have 5, it is called quintet. We should remember these things. The 2s plus 1 value determines the name of the state. It is a singlet, doublet, triplet, quartet or quintet depending upon the 2s plus 1 value of 1, 2, 3, 4 or 5. Then how to find out these term symbols? So let us take a simple example of D1, so that it comes later. So let me take it later, so I can find out term symbols for several electronic configurations. Before that one, let's look into how to determine the ground state term. There are certain rules we should follow while determining the ground state term. The terms are placed in order depending on their multiplicity values. That means 2s plus 1 value is given at most importance while determining the ground state terms. The highest value of 2s plus 1 will be the least energetic one. That means our most stable one. The most stable state has highest S value, and stability decreases as S value decreases. Then the ground state possesses the most unpaired electrons, that gives minimum repulsion. That means in order to have a larger 2s plus 1 value, so large number of unpaired electrons should be there, and when large number of unpaired electrons are there, it has to be essentially ground state. Means minimum repulsion, as a result maximum stability and less energy, lowest in energy. For a given value of S, the state with highest L is the most stable. Let us say I have two systems, both have the same multiplicity 2s plus 1. In that case, we have to give priority to highest L value is the most stable. And then if there is ambiguity for given value of S and L, then the J value has to be considered. The smallest J value is the most stable if the subshell is less than half filled. For example, D1, D2, D3, D4 will be L minus S is the most stable ground state, or if it is D6, D7, D8, D9, L plus S value of J will be most stable one. So that means if there is ambiguity for given value of S and L, the smallest J value is the most stable if the subshell is less than half filled. That is L minus S value has to be considered for J, and if the subshell is more than half filled, the largest J value is the most stable one. You have to consider L plus L value. For example, let us consider carbon here. We have P2 is there, it is the ground state term, and then we have 1D, 3P and 1S. And if you consider 3P has a triplet state, maximum S2S plus 1 value and ground state term among 1D and 1S. So then 1D is the most stable because L equals 2 as a S is same. So between them, if you consider highest L value, you have to consider highest L value is there among this one is for D. And now 3 has 3 states, 3P has 3 terms, 3P0, 3P1 and 3P2, and the smallest value of J is the most stable one as P2 is less than half filled. So 3P0 is less than 3P1 is less than 3P2 in terms of energy. So that means 3P0 is the least energetic one and is the ground term. So this is how you can write, and how we arrived this one through vectors I will show you in my next lecture. So now I have given some ground state terms for different electronic configurations, Pn and P6 minus n. So that means whether you have P1 or P5, and same thing D1 and D9 is something like that. They have the similar or identical terms. I can calculate those things and show you to make you familiar with identifying ground term or calculating the ground term from electronic configuration. That I would do in my next lecture. Then P1 and P5 have the same ground state term called 2P, and P2 and P4 have the same ground term 3P, and P3 has unique 4S, and P6 has 1S, and D1 and D9 have 2D, D2 and D8 have 3F, D3 and D7 have 4F, D4 and D6 have 5D, and D5 has 6S, D10 has 1S. If some of them have very similar terms, you can bring some correlation here. For example, if you look into D1 and D9 system, D1 is 1 electron is there, and D9 is 1 less than completely filled electronic configuration is there. Then we have 2D term. But if you look into D2 and D8, they have identical ground state term. That means 2 electrons are there in the d orbital, and 2 less than half completely filled electronic configuration is there. Then they have 3. That means it's very easy to remember. And then there is some correlation is there, some logic is there. Then look into D3 and D7. 2 electrons less than half filled electronic configuration D5, D3. So, 2 electrons less than a half filled electronic configuration, and then we have 2 electrons, 3 electrons more than, so completely filled electronic configuration. So, we have here, that means 2 electrons less than half filled, 2 electrons more than half filled, we have 4f here. And then if you look into D4 and D6, again one less than half filled, one more than half filled, we have 5d ground term. And then in case of D5 it's unique, 6s is there, and in case of D10 we have 1s is there. How we arrive at these things, and I will show you for several electronic configuration how to calculate, how to determine the ground term in my next lecture. Until then, have an excellent time reading about UV visible spectroscopy and enjoy the course. Thank you.